Hello. This recitation video will demonstrate through examples concepts of total probability rule, conditional probability, and multiplication rules. Task 1. The state police are trying to crack down on spending on a particular portion of the Massachusetts Turnpike. To aid in this pursuit, they have purchased a new radar gun that promises greater consistency and reliability. Specifically, the gun advertises plus minus 1 mile per hour accuracy 98% of the time. That is, there is a 0.98 probability that the gun will detect a speeder if the driver is actually speeding. Assume there is a 1% chance that the gun erroneously detects a speeder even when the driver is below the speed limit. Suppose that 95% of the drivers drive below the speed limit on this stretch of the Massachusetts Turnpike. So here I'm going to define the following events. So I'm going to say event D is that we detect a speeder, and event S is going to be that a driver is speeding. And so the given information that we just went over in the previous slide is that the probability that a radar gun detects speeding given a driver is speeding is 0.98. So that's the probability of D given S. The probability of D given S complement is the probability of a radar gun detects speeding given a driver is not speeding. So that's 0.01. The probability of S, event S, is the probability that a driver is speeding, and that was 0.05. And the probability that a driver is not speeding is 0.95. So what is the probability that the gun detects speeding and the driver was speeding? So here, this "and" is a keyword that shows that we're going to do an intersection. If it was "or," then we would have a union, but right now it says "and," so that's intersection. So we want to know the probability of event D intersect the probability of S. So in other words, the probability that the gun detects speeding and that the driver was speeding. So here, that the intersection equals the probability of D given S times the probability of S. So the probability that the radar gun detects a speeder given that the driver is speeding times the probability that a driver is speeding. So that equals, and I already wrote these, this is all given information from the previous slide here. So that's going to be 0.98 times 0.05, and that gives us 0.049. What is the probability that the gun detects speeding and the driver was not speeding? So here, that's going to be the probability of D intersect S complement. So S complement is that the driver is not speeding, and then D is that we detect speeding. So, and here we have an intersect again because we have this "and." So we are interested in this event and this event happening. So that equals the probability of D given S complement. So in other words, the probability that the radar gun detects speeding given that the driver is not speeding times the probability that the driver is not speeding. So that's going to be 0.01 times 0.95, and that gives us 0.0095. Part C. Suppose the police stop a driver because the gun detects speeding. What is the probability that the driver was actually driving below the speed limit? So here we're going to use Bayes' theorem. So we're interested in that the probability that a driver is a driver is not speeding given the event where we detect a speeder. So this, given Bayes' theorem, is going to be equal to the probability of D that we detect a speeder intersect the probability of S complement where the driver is not speeding, and then we're going to divide that by the probability of event D where we detect a speeder. And so here the denominator equals the probability where we detect a speeder and the driver is speeding, and the probability we detect a speeder and the driver is not speeding. So this is Bayes' theorem. So here we already solved all of these three individual values. So which really it's two different values because the numerator is the same as this value here. So this equals 0.0095. This is from part B, divided by 0.049. That's from part A, plus 0.0095. So when you simplify, you get 0.1624. And if my handwriting is a lot to look at, there's also a typed version of the answers, but it's basically the same exact thing that was handwritten. Task 2. Geographical analysis presented a study of emergency medical service, EMS, ability to meet the demand for an ambulance. In one example, the researchers presented the following scenario. An ambulance station has one vehicle and two demand locations, A and B. The probability that the ambulance can travel to a location in under 8 minutes is 0.8 for location A and 0.42 for location B. The probability that the ambulance is busy at any point in time is 0.03. Find the probability that EMS can meet the demand for an ambulance at location A. Okay, so my first step is just writing the information that I'm given. So here I'm going to define event M as that the ambulance is available, or in other words, not busy. Event A as that the ambulance can travel to location A in under 8 minutes. And event B is going to be that the ambulance can travel to location B in 8 minutes. And here, these two little lines just mean that I'm repeating whatever is above that. So it's just shorthand, so I don't have to write as much. But so B is stating that ambulance can travel to a location B in under 8 minutes. Okay, and we were also given that probability of A, which is that an ambulance can travel to a location A in 8 minutes, is 0.58, which we were given here. And then for location B is 0.42, which is written here. And then we were given that the probability that an ambulance is busy down here, this last bullet point, is 0.3. So the probability of M, which I defined as that the ambulance is available or not busy, would be 1 minus the probability that it's busy. So that would be 1 minus 0.3, which is 0.7. And here we want to find the probability that the EMS can meet the demand for an ambulance at location A. So here we're just interested in what I've circled in yellow, and I'm going to get back to this overall thing. But here for just part A, we're interested in the probability of A intersect M, which is the probability that the ambulance can travel to location A in under 8 minutes and that the ambulance is available. So since the probability that the ambulance can travel to location A, given that it's available, is equal to 1. So it obviously has to be available in order for it to travel to A. And likewise for B, but we can get into that later. Right now, we're only interested in this first situation. So here, we can just, to solve this, multiply probability of A, which is that the ambulance is available, that it can travel to location A in under 8 minutes, times the probability of M, which is that the ambulance is available. So that would be, probability of A is 0.58, and probability of M we calculated as 0.7. So 0.58 times 0.7 is 0.406, which is what we're interested in. Part B is finding the probability that an EMS can meet the demand for an ambulance at location B. So similar to what we just did, but here, however, we would be doing the probability of B intersect M, so that it's available and that it can travel to B in under 8 minutes. So here we have the probability of B is 0.42, and then we calculated this as 0.7, so you multiply those together and you get 0.94. Now, if the question was, what is the probability that EMS can meet the demand overall, then we would have the probability that it can meet the demand for location A and that it can meet the demand for location B. So if we were interested in just if the EMS can meet the demand, then we could add part A and part B together and get 0.7. Okay, task 3. Suppose that 4 inspectors at a film factory are supposed to stamp the expiration date on each package of film at the end of the assembly line. John, who stamps 20% of the packages, fails to stamp the expiration date once in every 200 packages. Tom, who stamps 60% of the packages, fails to stamp the expiration date once in every 100 packages. Jeff, who stamps 15% of the packages, fails to stamp the expiration date once in every 90 packages. And Pat, who stamps 5% of the packages, fails to stamp the expiration date once in every 200 packages. If a customer complains that her package of film does not show the expiration date, what is the probability that it was inspected by John? So, and here's a hint, is to draw a probability tree diagram. And so first, as a little tip, I like kind of color coding so that way I can tell, you know, what information pertains to each person. So here I've color coded that what's highlighted in yellow pertains to John. What's highlighted in this reddish color pertains to Tom. Green is Jeff, and blue is Pat. Just to kind of signal to me and keep that information straight. Okay, so here I'm going to define J as the event that the package is inspected by John. T is that the package is inspected by Tom. H is that the package is inspected by Jeff. P is that the package is inspected by Pat. Event S is that the package is stamped correctly. And event F is that the package is stamped, and I'm forgetting the P here, it should be stamped incorrectly. Okay, so first I'm going to draw tree diagrams for what I know. So here, event J is that the package is inspected by John. So if we go to the information we were given, we have that John stamps 20%, who stamps 20% of the packages. So here we have 20% or 0.2. And of those 20%, we were given that he fails to stamp the expiration date once in every 200 packages. So here for the fail event under John, that would be 1/200 that he fails to stamp correctly. So the remaining probability from if he were to stamp it correctly would be 1 minus 1/200, which is 0.995. And now we're going to do that for each person. So next is Tom. So Tom stamps 60% of the packages. So here, that's 60% of the packages. And of those 60%, he fails to stamp the expiration date once in every 100 packages. So 1/100 is going to be this F event under Tom, and 1 minus 1/100 is 0.99. And here for event H, that pertains to Jeff. So if we go here, Jeff stamps 15% of the packages. So that would be 0.15. And of those 15%, he fails to stamp the expiration date once in every 90 packages. So F here is going to be 1/90. So S, which is that the package is stamped correctly, is going to be 1 minus that probability, 1/90, which is going to give us 0.9889. And then last but not least, we have Pat, where Pat stamps 5% of the packages. so that would be 0.05, and of and fails to stamp the expiration date once in every 200 packages. So here the F under the PAT would be 0.005 or 1 over 200. So S, that it's stamped correctly, would be 1 minus that probability, which is 0.995. All right, so now that so far all we've done up to this point is just organize the information that we've been given, and we've been using our probability tree diagrams. Now let's go back to what we were actually asked. So here's the question stem. So if a customer complains that her package of film does not show the expiration date, so in other words, we're in this incorrect, that the package was stamped incorrectly, in other words, what is the probability that it is inspected by John? So in other words, we're interested in, so given that our package is stamped incorrectly, so what is the probability that it was stamped by John? So in other words, what is the probability of J given F? So that equals the probability of J intersect F divided by the probability of F. So in other words, the probability that the package was inspected by John and not stamped correctly. And then the divided by the probability that the package was stamped incorrectly or not stamped correctly. So here, let's just look at the probability of J intersect F. That's going to be the probability of J times the probability of F for J's situation. So here we have the probability that it was inspected by John was 0.2, and then the probability of that John had failed to stamp it correctly would be 0.005. So we're going to multiply those values together. And then we want to divide it by the probability that the package was stamped incorrectly. So we're going to add all of the situations that we have. So we have 0.2 for John times 0.005. And then we're going to add that to Tom's situation where we have 0.6. That's the chance that Tom had inspected the package times the probability that he failed to stamp it correctly. So that would be 0.6 times 0.01. And then the same for Jeff, which would be 0.15 times 0.011. And then plus Pat, the probability that Pat inspected it times this 0.005. So when you go and calculate all that math, you would get 0.001 divided by 0.008915, and that will give you 0.11217. Task 4. There is growing public support for marijuana law reform, with polls showing that more than half of the country is in favor of some form of marijuana legalization. However, opinions on marijuana are divided starkly along the political party lines. The results of a survey are shown in the accompanying table. In addition, assume that 27% of Americans identify as Republicans, 30% as Democrats, and 43% as independents. And then here we have the probability that you support marijuana legalization given you're a Republican is 41%. The probability that you support marijuana legalization given you're a Democrat is 66%. And the probability that you support marijuana legalization given the person is an independent is 63%. So here I listed this under the given information, and then I also included in the given information the probability that someone's a Republican, Democrat, or Independent. That was given here. And the events are defined on the left here. So R is Republican, D is Democrat, I is Independent, and S is support marijuana legalization. Part A. Calculate the probability that a randomly selected American adult supports marijuana legalization and is a Republican. So here we're going to have intersection because we have and. So the probability of S, where they support marijuana legalization, and they're Republican, that's R. So that equals the probability of S given R times the probability of R. So the probability that you support marijuana legalization given your Republican is 0.41 times the probability someone's a Republican is 0.27. So you multiply those together and you get 0.1107. Part B. Calculate the probability that a randomly selected American adult supports marijuana legalization and is a Democrat. So that would be the probability of S intersect D, which equals the probability of S given D times the probability of D. So in other words, the probability you support marijuana legalization given you're a Democrat times the probability you're a Democrat. And I keep saying you're, but really it's a person, is an American, is a Democrat, for example. So that would be 0.66 times 0.3, which is 0.1980. Part C, calculate the probability that a randomly selected American adult supports marijuana legalization and is an independent. So that would be the probability of S intersect I. So S is that the randomly selected American adult supports marijuana legalization and is an independent. So that equals the probability of S given I times the probability of I. So that would be 0.63 times 0.43, which yields 0.2709. What percentage of American adults support marijuana legalization? So here, that would be, so that's the probability of S. They support marijuana legalization. So that equals the probability that they support marijuana legalization and they're Republican, plus the probability that they support marijuana legalization and they're Democrat, plus the probability they support marijuana legalization and they're an independent. So in this problem, we only have three possibilities for the political parties, Republican, Democrat, and Independent. So if you add those together, that would give you the probability that you support marijuana legalization. So we already found all these three values. This was from part A. Probability of S intersect D is from part B, and then the probability of S intersect I is part C. So if you add those values together, you get 0.5796. Part E. If a randomly selected American adult supports marijuana legalization, what is the probability that this adult is a Republican? So here we're going to use Bayes' theorem. So that would be the probability that a randomly selected adult supports marijuana legalization given that they're a Republican. So that would be the probability, or sorry, I said that wrong. Given that they support marijuana legalization, what is the probability they're Republican? So that equals, using Bayes' theorem, the probability of S intersect R divided by the probability of S. So probability of S intersect R is from part A. We already solved that. That's 0.1107 divided by the probability of S, which we just solved in part D, which is 0.5796, and that equals 0.1910. And then here are the typed out solutions.